Hello everyone. I am Agasing Batra with our partner A.V.S.K Shlom, and we are from Bhavan Raipur, here to represent our project Astra Streak, which is a deep learning model for detecting near-Earth, fast-moving asteroids. Now, coming to the background or the motivation of our project. In 2013, a 19-meter asteroid exploded over the Russian city of Chelyabinsk. It resulted into the release of 500 kilotons of TNT equivalent energy, and it destroyed 7,000 plus buildings and 1,500 people were injured. So you can see how much damage even a 19-meter asteroid can do. Now, in 2024, also, there were two incidences where asteroids were detected just before entering the atmosphere. Those are 2024 UQ and 2024 BX1, exploding over Pacific Ocean and Germany, respectively. Now, what is the problem with fast-moving near-Earth asteroids? Now, they are very small in size and they're very faint. So they reflect only a fraction of sun's light, which makes them harder to see. And their angular speeds are more than 5 degrees per day. So they become more difficult to detect. And even the big organizations, the big space organizations like NASA, has detected only 0.1% of the asteroids, which is smaller than 44 meters in diameters. So we can see that these asteroids, if they remain undetected, can do a lot of damage, and it is important to detect them at an early basis. Now, coming to what we have done, now coming to the hypothesis, we have created our project Astra Streak by using the CNN or the convolutional neural network architecture with base layer efficient at B5. We have used image preprocess techniques like Gaussian deep blur, Canny detection, Hogline transform, and morphic masking, and the parametric equations to detect the coordinates of the asteroid and to predict the future short-term coordinates, like where the asteroid will be in the next few hours. Now, methodology will be explained in detail by my partner.
So moving towards the methodology, we are using convolutional neural network as it is best for extracting features from the images, and also it can learn patterns as fast as possible. So we have a training data set of 12,000 images with 6,000 of streaks and 6,000 of stars. And our model consists of base layers of EfficientNet B7, which is pre-trained on ImageNet V1 dataset. And we have 4 more custom layers starting from 512 neurons to 64 neurons to get as much as parameters which we can get from the images. So we have used sigmoid activation so that we can get the prediction probability of streak images and star images between 0 and 1. So the first graph shows that the features extracted from our model for the streak and stars respectively. The yellow one shows the features extracted from the streak images, and the purple one shows the features extracted from star images. And the second figure shows the frequency of the features extracted from the streak images and star images. So after detecting the streak images in the fit images or the images provided by the observatories, we apply our image preprocess techniques like adaptive Gaussian blur, morphic masking, Canny detection, and AstroBite or WCS module. So we have validated this model on Apophis and Astro detected by NASA in year 2004. So first we took the 8-bit log scale image of the Apophis asteroid. So you can then we apply Gaussian deblur function. So while applying the Gaussian deblur function, you can see there is a huge variation between the 8-bit log scale image and the denoised image. So you can see the image is way more clearer. So after getting the denoised image, we apply morphical operation to mask the area of the Astra Streak. This morphic masked image will now used for Canny detection, where we detect the edges of the masked Astra Streak. So after detecting the edges, we apply Hogline transform to detect the max possible line that could be found between this edge detected image. So this line now will be used for getting the centroid of this line, so that we can use AstroBite.WCS module to detect the RA and DEC current coordinates of the fast-moving Astra Streak, and further calculating the angular velocity using parametric equation. So in the parametric equation part, you can see the first equation tells that omega equals to length of the Astra Streak in degrees upon the exposure time. The exposure time is provided by the observatories in their header unit list. So by calculating this, by calculating the asteroid streak length and the exposure time, we get the angular velocity. And the second formula gives us the precise velocity of the precise velocity of the fast-moving Astra Streak using uncertainty of velocity formula. So from this, we can get the precise velocity and use it for future coordinates prediction. So moving towards the experimentation part, we have used 2D Gaussian function to generate more synthetic streak, as the real data is very less for fast-moving Astra Streak. So using this, we can generate random intensity, random brightness, and random length synthetic streak, which will increase the robustness of the model so that it can predict the Astra Streaks way more easier. And also we have used way more pre-trained models, like starting from VG16 to EfficientNet B7, from which we concluded that efficient B7 is one of the accurate, and it gave us the means quality parameters for detecting an fast-moving Astra Streak in an image. So in the result, we got that when we tested it over the result, the Astra Streak model got 98.85 accuracy when tested over real data set, showing that it predicted 1200 true positive, 1123 true negative, and 27 false positive, and achieved a recall of 0.9885, precision of 0.978, and overall the F1 score of 0.9889, demonstrating that it is very high sensitive in detecting fast-moving Astra Streak in the data provided by the observatories. So the novelty will be explained by my partner.
Now, coming to the novelty or the advantages of our project and how our project is unique. Now, in our project, we are able to calculate the coordinates of the asteroid, and we also are able to predict the short-term future coordinates of the asteroid. Now, this model is basically made to be run on low-end GPUs, so that even the amateur astronomers and the individual researchers who are not part of any big organizations can also do their research, because in the history there have been certain times when the asteroids are detected just hours before falling, and before they are detected by the big organizations, they are detected individually by the amateur astronomers. Two of these incidents are 2008 TC3 and 2014 AA. So coming to the future prospects of our project, which is what we intend to add to our project to make it better. So we intend to include a wider range of near Earth objects to our dataset. We intend to incorporate with the NASA's DART system, which is double asteroid redirection test, which is used to redirect the asteroids if it poses a risk for the Earth. Now we'll study Kepler's orbital mechanics and check the exact trajectory of the asteroid to see if it poses a risk. Now we can also check if it is harmful for the ISS, the International Space Station, or the human-made satellites in the space. Now we can also incorporate multi-scale velvet masking and edge detection techniques to enhance the accuracy in the complex data sets. Now, coming to the conclusion of our project, what we are doing is that we take the data from the observatories, we process it with the image preprocess techniques, we make it clear, then we detect the streaks in them, which is the paths the asteroids take, so that we can know of the asteroid, and then we are able to predict the coordinates of the asteroid and where the asteroid will be in the short term or the near future. Now, the main thing of our project is that it runs on low-end GPUs. Now, this was our project, and coming to the recognition of our project or our recent achievements. We got selected for IRIS Cohort 1 2024-25 and presented our project in Delhi. We won the gold medal in INSEF regionals. We won the silver medal for INSEF Nationals 2025. And we also got selected for A.V.S.K held at Tunisia, Africa. Now, this was all about our project. Thank you.
Thank you.